Greetings. In this problem, we're going to titrate 50 mils of acetic acid with a concentration of 0.15 moles per liter with NaOH that has a concentration of 0.15 moles per liter. And we're going to go from 0 mils to 70 mils. And we're going to calculate the pH. Now, the very first thing we have to do is ask ourselves what volume of base gets to 0.3, okay? Because the equation we use depends on that. The first point is trivial, that's the pure acid. But once we start adding base, we need to know, are we in the buffer region, the equivalence point where we've converted all the base to a salt in the stoichiometric proportions, or in the excess base region, okay? So to do that, we say that at the equivalence point, the moles of the acid is equal to the moles of the base. And the moles of the acid is the molarity of the acid times the volume of the acid, which is what we started with. And that's equal to the molarity of the base times the volume of the base at the equivalence point. And it's only at the equivalence point that these two are equal. And that's what we're trying to find out. What is this volume that gets us to the equivalence point? So we can now say that the volume of the base at the equivalence point is equal to the volume of the acid times the molarity of the acid over the molarity of the base, okay? And that's equal to, we started with 50 mils of acid, and our molarity of our acid is 0.15 moles per liter, and the molarity of the base is 0.15 moles per liter, and so that is 50 mils, and this makes sense, okay? We've started with equal concentrations, so the equivalence point will come at equal volume. So we just calculated that the volume at the, let me get this in black, the volume at the equivalence point is 50 mils, and so anything less than that is the buffer region, at that is the equivalence point, and greater than that is the excess space. Now the first value, so what we're going to do is we're going to make a table here, okay? And in the table we're going to have the volume of the base added and the pH. The first value is trivial and we didn't have to calculate this, and that was before we added any base. We have a pure acid, and we could have done this in the last chapter, and we know that pH equals minus the log of the hydronium ion concentration, and we know that if the initial acid concentration is greater than 100 Ka, we don't have to do the Rice diagram or the quadratic formula. We can use the shortcut from complete the square, and we know that Ka, Ha initial will be the solution of the Rice diagram. And so we can now bring this into minus the log of Ka is 1.8 times 10 to the minus 5, and the initial is 0.15. And when we bring out our calculator, we get a value of 2.34. So our initial concentration is 2.34. Okay, now our concentration, our initial pH is 2.34. Okay, now we're 20 mils, okay, and 20 mils is less than the 50 at the equivalence point, so we're in the buffer region. And we know in the buffer we have pH equals pKa plus the log of the salt A minus over HA. And what we know here is it took 50 mils to neutralize each other, so this is equal to the pKa, which is minus the log of 1.8 times 10 to the minus 5 plus the log. Now, remember from earlier that we can use the ratio. In other words, it took 50 mils to neutralize all of the acid. We've added 20 mils. So I'm going to put this 50th here, although I probably shouldn't. So we've neutralized 20/50ths of it, and 30/50ths of it is still unneutralized, okay? So this becomes the log of 2/3, okay? And that would be equal to, so this is equal to 4.74 minus 1.76. Oh, notice that this is a fraction because we haven't made it to the half equivalence yet. And this would be equal to 4.56. So at 20 mils, we're at 4.56. Now the next value, so we just did the 20 mils, and now we're going to do the 25 mils, okay? And at 25 mils, we've neutralized half of it. And we know that when we've neutralized half of it, pH equals pKa plus the log of A minus over HA. But since we've neutralized half of the original, we're 25 mils in when it took 50 to go all the way. These equal each other, and so this is all equal to 0 because the log of 1 is 0. So pH equals pKa. So at 25 mils, it's 4.74. The pKa value for acetic acid. Now we're at 50 mils, which is the equivalence point. So we've formed the salt. We've formed the conjugate salt of acetic acid. But we've done two things. We've formed the salt and we've diluted it. So we know that, that for the salt of an acid, the hydroxide concentration is equal to square root of Kw over Ka, conjugate acid-base pair from the last chapter, times the salt anions concentration, the conjugate base of the weak acid, A minus, acetate. Okay? And this is equal to K square, that's the hydroxide. So the hydroxide is equal to the square root of Kw over Ka, and the amount of acetate is either the molarity of the acid times the initial acid concentration, or the molarity of the base times the volume of the base at equivalence, because that's the definition of the equivalence point. They're equal. So I'm going to use the base. So I'm going to say that this is the molarity of the base times the volume of the base at equivalence. But I could have used the molarity of the acid times the volume of the acid that we started with. But we've not only neutralized the acid and converted it to its salt, we've also diluted it. So we have to divide by the total volume, which is the volume of the acid that we started with and the base that we added to neutralize it, okay? And so this is going to be equal to, the hydroxide concentration is going to be equal to the square root of Kw, which is 10 to the minus 14, over 1.8 times 10 to the minus 5. And the acetic acid had a concentration of 0.15 moles per liter. And we added 50 mils of it to reach the equivalence point. That's where we are right now. And we added it to 50 mils of acetic acid. So we have 100 mils total in the bottom. And when we do this, we get 6.45 times 10 to the minus 6. Now, I find it easiest just to solve for POH when I'm in a salt region and then just at the end convert it to pH. You could solve this many ways you want. So POH equals minus the log of OH, which equals minus the log of 6.45 times 10 to the minus 6, which is equal to 5.19. And we know that pH equals 14 minus POH, which is equal to 14 minus 5.19, which is equal to 8.81, because pH plus POH equals 14. Okay, so at 50 mils, we have a pH of 8.81, and notice that the equivalence point is basic because we have the salt of a weak acid, which is basic. Now we're going to go for our final point at 70 mils. Whoops, let me put on the dark. 70 mils. And we've gone past the equivalence point. We've gone 20 mils past the equivalence point. And basically speaking, in the excess base region, the hydroxide concentration is the moles of hydroxide excess divided by the volume total, okay? And so this is equal to the total moles of hydroxide we added, which is the molarity of the base times the volume of the base, minus that which was consumed, which was the molarity of the base times the volume of the base at the equivalence point, okay? And we can see that there's 20 mils extra because we've added 70 and 50 was used up, okay? And then that is divided by the total volume, which is the volume of the base, the 70, plus the volume of the acid, which happened to be 50 also, okay? So now this is equal to the molarity. Now I can factor out the molarity of the base, and so that's equal to 0.15 moles per liter, and then that's times the 70 mils that I added minus the 50 mils that were consumed when it reacted with the acid. So we have 20 mils excess, which makes sense. And that's divided by the volume of the base, which is the 70 mils. And it just happens to be that there's this 50 mils in the acetic acid, but the plus 50. Recognize that this 50 is the 50 mils in the Erlenmeyer flask at the beginning. And I now do my calculations, and I come up with 0.025 molar. So POH is equal to minus the log of 0.025, which is 1.6. So pH equals 14 minus 1.6, which is 12.4. And so now I've calculated the pH for all the different regions of the titration curve as a function of the volume of base added to an acid.